Hey folks, welcome back to Calculus 1. I'm Dr. Jeff Groh. Today we're going to talk about related rates. Let's begin with an example. Let's suppose that I have oil dripping down into a puddle. The puddle is going to be a perfect disk for the sake of this argument, and what is more, the puddle is going to have a constant thickness of 2 millimeters or 0.2 centimeters. Let's assume that the rate at which oil is dripping down into the puddle is 2 cubic centimeters per minute. Not very fast. However, the more this oil drips down and into the puddle, the wider the puddle is going to get. What I want to know is how fast is the radius changing when the radius is 10 centimeters. As you can see, the radius will depend upon how much volume of oil is present. The first step to solving this problem is to find a relationship between the volume and the radius. In this case, the volume is that of a cylinder, since the fluid more or less takes the shape of a cylinder. The volume of a cylindrical can with a radius r and a height h has the formula pi r squared h. This is consistent with something called the theorem of Pappus. The theorem of Pappus says that if you take some area, pi r squared, and sweep it h units in the direction of the normal vector sticking off of that surface, then you end up with a volume of that area times how far you swept it. In our case, h is constant. But now we have a relationship between the volume and the radius, but each of those is a function of time. The volume changes with time, and the radius changes with time. If we take the derivative on each side of this equation, we should take the derivative with respect to time. When we do that, we still have this 0.2 pi. We need to think of r squared as a composition. The derivative must be taken implicitly, since we're taking the derivative with respect to time. We'll get 2r times dr dt, where the dr dt comes from the chain rule. It is at this point that we need to plug in the r equals 10 centimeters. Not before. If we plug in r equals 10 in the volume formula, the volume will be constant, its derivative will be 0. You have to plug in those values after you calculate the derivative. Now, the volumetric rate of change is given to be 2 cubic centimeters per minute. We'll plug in 2 for dv dt. The only unknown after we plug in r equals 10 will be dr dt, the rate of change of the radius. So we'll get 2 equals, let's see, we have 0.4 pi times 10. That's 4 pi times dr dt. We can cancel a 2 from each side, and dr dt will be 1 over 2 pi, and the units of this answer will be centimeters per minute. R is denominated in centimeters and T in minutes, centimeters per minute. In our next example, we're going to have a cone that has fluid being added to it. The fluid level is going to be rising with time. It has some depth h. H is going to be a function of time. So is the radius. Let's suppose the radius of the cone generally is 3 centimeters and the height is 7 centimeters. I want to know if you have 1 cubic centimeter per second being added into this cone, how fast is the height rising, h, when h is 3 centimeters? So first, we need to know what the relationship is between volume, radius, and height. In particular, for a cone with a radius r and a height h, the volume is 1/3 pi r squared h. In this case, though, there's a relationship between the radius and the height. You can see that if we drop an altitude, we'll have a couple similar triangles. For similar triangles, ratios of corresponding sides are equal. So we will have r divided by 3 equals h divided by 7. H divided by 7, r divided by 3. Which means we can eliminate one of these variables. Let's eliminate r. R is going to be 3/7 the height. And so in our volume formula, 1/3 pi r squared h will have 1/3 pi times 3/7 h quantity squared times h. Now 3 squared is 9, divided by 3 gives you 3. 7 squared is 49. And we'll end up with an h cubed. Now the volume will depend only on the height, and dV dt, which we know to be 1 cubic centimeter per second, is 3 pi over 49 times 3h squared dH dt because of the chain rule. And it is at this point that we substitute h equals 3 centimeters. So dH dt will be 49. We'll have 3 times 3 times 3 squared. That's 9 times 9, that's 81. And the units are centimeters per second. In our next example, we're going to have an observer on the ground. Let's say 2 miles down the way there's an airplane. You gotta love the artistry. The airplane is moving at 1/5 mile per second. And it is at 0.9 miles altitude. I want to know the rate of change of angle. To solve this problem, some things that seem constant need to be replaced for the variables that they truly are. This object is moving, The airplane is moving, which means the x position here is a variable. What isn't changing is the altitude. So what we have is opposite and adjacent on a right triangle. What does that tell you we should use? Tan theta is 0.9 divided by x. Both x and theta are functions of time. We'll calculate the derivative with respect to t, time. We'll get secant squared of theta times d theta dt equals negative 0.9 over x squared times dx dt. Remember, the derivative of 1 over x is negative 1 over x squared. By the chain rule, you need to multiply by the derivative of x with respect to t, and that's where the dx dt comes from. What you're looking for is d theta dt. In all of these derivative formulas that I've had you memorize, theta is assumed to be in radians. The answer will have units of radians per second. Trigonometric functions output unitless ratios. Tangent is opposite over adjacent. Miles over miles is unitless. Secant squared is also unitless. D theta dt has the units of radians per second. Radians are the unitless unit. When we defined radians way back in trig, we had a circle with an angle theta, radius r, and arc length s. Theta was defined to be, in radians, s divided by r, arc length divided by radius. Length divided by length is unitless. Radians are the unitless unit. The left-hand side really has units of 1 divided by seconds. What are the units on the right-hand side? 0.9 has units of miles. dx will have units of a change in distance or in miles. So you have miles squared. X squared has units of miles squared. That cancels out. And dt has units of seconds. So it too has a net unit of 1 over seconds. So the units match on each side of this equation. All we have to do is plug things in. One thing we don't know at this point is what secant theta is, but we can figure that out because secant is hypotenuse over adjacent. The length of the hypotenuse is going to be 2 squared plus 0.9 squared, which means secant theta will be the square root of 4.81 divided by 2. dx dt was the speed of the plane. That was 1/5 mile per second. X was 2 miles. Secant squared then is going to be 4.81 divided by 4 times d theta dt, which is what we're trying to solve for, equals negative 0.9 divided by 2 squared, which is 4, times 1/5 mile per second. Multiplying both sides by 4 and dividing by 4.81. But if the airplane really is flying in towards the observer, the rate of change of x should be negative. Negative times negative makes a positive. We'll get d theta dt equals 0.9 divided by 5 times 4.81, and the units of this will be in radians per second. How do we convert this answer to degrees per second? One has to keep in mind that pi radians is 180 degrees. In this case, my calculator gives me 2.14 approximately degrees per second. And the angle will be positive, will have a positive rate of change. It'll be increasing because the object is moving towards the observer. In our next problem, suppose we have a ladder leaning up. Here you are hanging onto the ladder for dear life, leaning up against a wall of a house. And let's suppose that here we have Fido, and Fido is going to latch on and pull. Here's his tail. He's going to be pulling really hard. He's going to latch on and pull the ladder this way. Now we're going to assume, for the purposes of this example, that the top of the ladder always remains in contact with the house, but it has to go down as the ladder is pulled out away from the house. This is Fido. Now, here's the idea. Fido can pull at 1 foot per second. How fast is the top of the ladder dropping? When the top of the ladder is 5 feet off of the ground. Let's suppose that this is a ladder that has a lucky 13-foot length. Also, how fast is the ladder moving when it hits the ground? On all of the problems that we've done so far on this section for related rates, we've had to come up with some kind of a relation, an equation, whether it be using similar triangles or definitions of trigonometric functions, or in this case, it should be clear that we need to use the Pythagorean theorem. We have a right triangle. X is a variable. It depends upon time. Y is a variable. It too depends upon time, though the length of the ladder is a constant 13 feet. The relation that we need to write down is x squared plus y squared equals 13 squared. It's this equation that we need to take the derivative of. 2x times dx dt plus 2y times dy dt equals 0. The dx dt and dy dt come from the chain rule. We can multiply through by 1/2 and then solve for dy dt. Both questions relate to how fast the top of the ladder is dropping. You can see then that moving this term to the other side and dividing the y off, dy dt is minus x over y dx dt, where dx dt is how fast Fido is pulling. He's pulling the end of the ladder out at 1 foot per second. How fast is the ladder dropping? First, when the ladder is, when the top of the ladder, when y is equal to 5. Now, if y is equal to 5, what's x? If y is 5, x can be determined from this equation. By the way, 5, 12, 13 is a Pythagorean triple. And so to solve the first part, dy dt is going to be minus 12 over 5 times 1. So the top of the ladder, when it's 5 feet off the ground, will be moving down, that's why it's negative, at a rate of about 2.4 feet per second. To answer the second part will require a little more analysis. The equation dy dt equals minus x over y dx dt is still true. It's just that we need to solve for y as a function of x. Check this out. dy dt is going to be minus x over the square root of 169, which is 13 squared, minus x squared times dx dt. When y is equal to 0, x is going to 13. So what we need to do is we need to take the limit as x goes to 13 from the left, from below. If we choose values of x bigger than 13, we get a negative under the radical. That gives us complex answers. We have to go from the left. Dx dt is still 1. The numerator is going to negative 13, but the denominator is going to 0 from the right, which means then that the limit is minus infinity. Yes, the top of the ladder is going to go faster than the speed of light, and it's going to smack the ground, and the only thing left is going to be a little pink cloud that used to be you. So Fido, bad dog. Now, obviously, something physically has to break down before that happens. There's no way that you can go faster than the speed of light. So either the top of the ladder is not going to maintain contact with the wall, or the bottom won't maintain contact with the ground, or you won't be able to continue pulling at a constant rate of 1 foot per second, because eventually it requires too much energy to do that, to maintain that constant rate. So this is physically impossible, but that is the correct mathematical solution under the assumptions that we have made. A similar problem occurs if we have a dock with a winch right here. There's a crank, you can crank in a cable. Out here on the water we happen to have a boat. And what we're doing is we're going to pull the rope, the cable in, let's say at 1 meter per second. And the point of attachment on the boat is, let's say, 3 meters above, let's see, 3 meters below the winch. And what else do we know? Let's suppose that this is 20 meters out. I want to know, if this is moving in at 1 meter per second, how fast is the boat moving in towards the dock? We need to define some variables. A lot of students don't understand the importance of the step of defining the numbers, of defining the variables in the problem. In this case, this horizontal distance is changing while the amount of rope let out is also changing, whereas the other side is just 3 meters. Once you've defined the variables, you can then write down relations between them. In this case, it looks like another application of the Pythagorean theorem. 9 plus x squared equals r squared. We can take the derivative at this point. 2x times x dot, remember x dot is dx dt. This is Newton's notation for derivatives with respect to time. Equals 2r times r dot. This other thing being a period, I'll just erase it. Multiply both sides by 1/2. dr dt is given. It's dx dt we have to solve for. So x dot is going to be r divided by x, r dot. R dot being defined to be 1 meter per second. We want to know how fast the boat is coming in, dx dt. X is equal to 20. If x is equal to 20, what is r? Well, that's determined by Pythagorean theorem. So 20 squared plus 3 squared equals r squared. 20 squared is 400. 3 squared is 9. R squared is 409. So the value of r will be the square root of 409. X dot then will be the square root of 409 divided by 20 all times 1, and the units are meters per second. My calculator gives me 1.01 meters per second. Now, I want to change this just a little bit and ask, how fast is the boat moving when it hits the dock? We still have x dot equals r over x, r dot, and r dot is still 1. R, on the other hand, is the square root of 9 plus x squared. And we want to find the speed, dx dt, in the limit as x goes to 0 from the right. The top is going to 3. The bottom is going to 0 from the right. Remember, 1 over tiny is huge. This thing's going to infinity. So as the boat gets reeled in, it goes really, really fast at the end and goes past the speed of light, and there it is. It hits the dock, and there's nothing left but a little brown cloud that used to be the boat. So obviously, this can't happen in reality. Again, you won't be able to maintain 1 meter per second. The boat won't stay in the water. It might be lifted out of the water. It just can't happen in real life. So, under these idealized conditions, as the boat hits the dock, it's moving way past the speed of light at an infinite number of meters per second. I only want to do one more example right now because we're going to have a lab and we'll do more examples then. I do remember that when I took calculus, this was one of the subjects that I had difficulty with only because it was so unexpected and new. However, once you get the hang of it, all of these problems seem the same. Let's suppose that we have a lamp. And this thing is 15 feet off of the ground. Here we have a person who is 5.5 feet tall, walking at 3 feet per second towards the lamp. Let's suppose this person casts a shadow. I want to know how fast the tip of the shadow is going. So, to solve this problem, we do need to use similar triangles. But the key difficulty in solving this problem is to define the appropriate variables. The position from the person to the lamp is certainly a variable. We'll call that x. But so is the position from the tip of the shadow to the lamp. Let's call that big X. Then we need something that relates little x and big X, because we need something that takes this one rate and will give us this related rate. So we'll use similar triangles. Similar triangles tells us that the distance of this, the length of this side, which is big X minus little x, divided by 5.5 is equal to big X divided by 15. Both little x and big X are functions of time. Now, let's cross-multiply and simplify this expression before taking derivatives. We'll have 15 times big X minus little x equals 5.5 times big X. Distributing, we'll have 15 big X minus 15 little x equals 5.5 times big X. Let's move some terms around. When we move the 5.5 big X to the left-hand side, we'll have to subtract. We'll get 9.5 big X equals 15 little x. We'll take the derivative now. 9.5 dx dt is 15 d little x dt. d little x dt we said was 3 feet per second. So dx dt is the one thing we don't know. We'll divide the 9.5 off. The answer then is, according to my calculator, about 4.74 feet per second. One interesting thing to note is that this value is true regardless of the value of little x, regardless of how far the person was from the lamp. So while the person is moving at a constant speed, the tip of the shadow will also be moving at a constant speed, but faster. After all, by the time the person gets to the lamp, the shadow has to get there too, but it had to cover a larger distance.